Okay, great. So yeah, originally the title was Reduction and Completeness, but I received some feedback during review, and I decided to have a more relaxed talk, and I'm sure everyone's brain has already been fried from the 20 different incorrectness logic we have seen today. And so I didn't add a lot of math in there, but I would give an overview of how to work with Kleene algebra and how does it connect to program logic and what are the future works that we can do in this respect. And the topic and the title is when algebra marries program logic. It's slightly inaccurate. It's when algebra proposes to program logic, because there's still plenty of work to do, and I believe there's a promising aspect of this. And so let's recap on the core semantics of program logic, which you have already seen 20 times. You start with some precondition, you execute some program on this, and you reach some ending values. And in this talk, I will call them codomain, and some people call them range of the function. It's the same thing. And then you compare the codomain of the function with some postcondition. If the codomain is contained within the postcondition, then we got Hoare triples. And if the codomain contains the postcondition, then we got incorrectness triples. And so you see, like the building block of a program logic, you have program and you have predicates, and then you need to compare codomains, right? And this is where TopKAT came in. And TopKAT consists of 3 different components. It contains top, ka, and te, right? So ka is ka, and te is test, right? So for Kleene algebra, it's an algebraic system for regular expressions. So it gives you a lot of the desirable structures that you need to program. For example, branching, sequencing, and iteration. But in regular expression, branching and iteration are non-deterministic. That is, you cannot guard them by a condition. And that is where tests come in. So tests are intuitively predicates on memories. And they are basically conditions that guards the program intuitively. And with that, you can get conditional branching and conditional iteration, which corresponds to if statement and while loops. And besides that, because tests are predicates on memories, they can also serve as predicate within like the program logic. Right? If we look at Kleene algebra with tests, they already have most of the things that program logic needs. So we can think of Kleene algebra with tests as an imperative language with some extra features. For example, it can also express predicates, and it has non-determinism. And in fact, with Kleene algebra with tests, it's already enough to encode Hoare logic, and this is a very early result by Cozen. And so another nice thing about cat is that we can put cat pictures on our slides, and this started a lot of cat meme within the community. And in that vein, TopKAT is basically a fancier cat. And no, that's not true. Unfortunately, as a computer scientist, I sometimes do need to do computer science instead of posting cat picture all the time. So top are for codomain comparison, which is the last step we need to model program logic. And notice in this talk, we will only talk about codomains, but for domains, it's the same. For domain, you are basically doing like the backward reasoning that people have talked about. And the system can also be extended. It doesn't need to be extended. It can also model like domain comparisons. But we only show codomain as examples. So here are 2 simple programs, right? So you only have 2 memories. Program P sends both memory into memory 2, and program Q doesn't change the input memory. And we cannot directly compare them, even though program P has a smaller codomain than program Q, right? We need something to help us extract the codomain. And this is where top comes in. So in here, I imagine top as a complete relation. I define top as a complete relation. And when you compose a complete relation with another relation, it kind of normalizes the domain and the internal transition within the relation. And in the end, you can compare the codomain once you pre-compose with top. And if you post-compose with top, you get the comparison between domains. And if we look at the semantics of program logic, they're basically domain comparisons, right? And the Hoare logic says if you guard by P and then execute guard by B, then execute P, its domain should be smaller than the domain of C. And that's exactly the encoding of Hoare logic, which top BP, which is extracts the domain codomain of BP, and top C, which extracts the codomain of C. And similarly, for incorrectness logic, you just need to switch the inequality. And this encoding turns out to be surprisingly successful because we were able to derive all the proof rules of incorrectness logic and Hoare logic just with this encoding. And by proof rule, I mean like structural proof rules, which exclude assignment rule, because in here we don't have definition of assignment. And this is a very nice story for TopKAT, right? I talked about this on Popo 2022, but actually I was a bit hesitant. Because our intuition are fully based on relational model, and it's a very restrictive form of relational model, right? The top elements are required to be the full element, which is like the complete relation. But why does the algebra able to encode like these two very powerful logics, right? These two logics are relatively complete, which basically means like they can derive anything with respect to relations. And indeed, we have a way to characterize how powerful a certain algebra is. It's called completeness. So for an algebra to be complete with respect to its relational model, it says all the inequality that holds in every relational interpretation can be derived from the algebra. In other words, the algebra is powerful enough to prove all the inequality that holds in every relational interpretation. If this holds, then it gives us an explanation of why TopKAT is so powerful, even though our intuition is based on like a very restrictive type of model. And typically, how do we prove completeness in Kleene algebra, in the like extensions of Kleene algebra? We start with a theory, and we develop a complete interpretation for that theory. And this is typically the hardest part of doing the completeness proof, and we will see later. And then we embed the complete interpretation into relational interpretation. Basically, going from a complete interpretation, we construct certain relations that preserves all the equalities within the complete interpretation. And for Kleene algebra, the complete interpretation is a regular language. So it basically computes a regular language from the regular expression. And this is only proven in the 1990s, which is way after when regular expression was introduced. So as you can see, it's a very hard proof. And then we can embed regular languages into some relations. And this actually predates the completeness of Kleene algebra. This is proven in 1970s. So you can see like the first part is really the hard part. However, for Kleene algebra with test, its complete interpretation are program traces. That means two programs are trace equivalent if and only if they can be their equivalence can be proven by the theory of KAT. And this it's proven, I think, in the early 2000s. Why is it this fast, whereas the completeness of Kleene algebra took like 20 years? It's because they use something called a reduction technique. So instead of proving everything from scratch, it basically reduces the completeness of program trace into the completeness of regular languages. And in this way, people don't need to prove completeness of program trace from scratch. They can leverage the completeness of regular languages to prove the completeness of CAT. So however, in this case, we need a reduction both from CAT terms into Kleene algebra terms and a reduction from program traces into regular languages. That's like the previous proof that most people, most literature follows. And then we can embed the program trace into input-output relation. That is very easy. And we want to do the same thing with TopKAT, right? Because we have this very powerful algebraic system, and we don't know why. Because, maybe it's complete with respect to relational model. Then it explains why it can model the entirety of proof rules of incorrectness logic and Hoare logic. And we were able to streamline the reduction so much that the reduction no longer needs to mention the semantics. We can directly do the reduction on the algebra. And this is a very nice proof using properties of universal algebra, which is what I used to want to focus on, but now it's this. It's fine. And the complete interpretation of TopKAT is program traces with top, which is like the full element, and sometimes are called havoc. So it's the element with every single trace possible. So this element can execute anything. And the completeness becomes a corollary of the reduction in here. So we can push the reduction down each step. And turns out if we want to push the reduction down for relational models, everything blows up. Right? Indeed, relational model turns out to be incomplete with TopKAT. And this is inequality that we discovered in 2022. This inequality is true for every single relational model, but it's unprovable using the theory of TopKAT. And later, Damien Paul and Yana Wagemaker in 2023 proved that if you add this into as an axiom, then TopKAT is indeed complete with respect to relational model. But I was not satisfied, because look at this picture. When we were able to derive the incorrectness logic and Hoare logic proof rules, we don't need that additional rule. And why is that? Indeed, I think we later discovered that if we are doing things with all inequalities that holds in every relational interpretation, it's an overkill, right? We are only using the top element to extract domain and codomains. So we later showed that if we restrict the inequalities that we are looking at with codomain and domain comparison inequalities, which are like pre-composition with top or post-composition with top, then we can actually prove the completeness by using the language interpretation or the complete interpretation. And finally, we can say always has been. Okay. So yes, so it's all algebra at this point, and we have proven that TopKAT is powerful enough to encode both incorrectness logic and Hoare logic, and we have shown why it's so powerful, and using like the theory of TopKAT. And then why is TopKAT useful? Why are we interested in this? And I will give some perspective on what future work and how do I envision TopKAT is going to be used. But first notice that this is a question you never want to ask because you will upset a little cat with a top hat. Look at how sad that little guy is. Seriously, why would you doubt his usefulness? So for now, I think a good use of TopKAT is a semantic foundation. So if in your semantic domain, you find that there's a top element, then you automatically get incorrectness logic and Hoare logic out of it. So I think that's kind of nice, and it's a very fast thing to check. Unfortunately, a lot of the interesting domain doesn't satisfy this property. For example, probability. There's no largest probability, right? The probability are always sums to 1, and if you compare two probabilities, there's no one that is there's no largest probability distribution. Yeah, okay, and I also want to encode more program logic features like relational reasoning, which has already been done, but we recently proved that their system is undecidable. And this will be a talk in Netherlands by Arthur D. Amorim. If you are there, it's very good. And I also want to encode notions of separation and abstract interpretation and symbolic executions. And for separation in particular, I think it might help us to speed up tools developed around Kleene algebra. And finally, as an automation tool, I don't know why the tool looks like this. It's supposed to be pretty big. So as an automation tool, so I was hoping, like, because Kleene algebra are famous for being decidable and usually very fast, so can we automate some of the decision procedure of program logic using algorithms within Kleene algebra and Kleene algebra's test? And finally, it gives us more chance to put cat memes in our slides. Okay, great. Yeah. Yeah. Thanks.
I'm wondering, very good talk. Thank you so much. I wonder if you explore TopKAT.
Oh yeah, right. So I think that's a very good thing to explore because like the reachability property can be expressed using top in a very natural way. But yeah, we just didn't have time to do that.
I was asking to myself, is a cat ad hoc or not? So to answer this, I ask you a question.
Yeah.
If I change all logic to Mueller-Mana logic, which is all logic with for total correctness.
Oh yeah.
What happens?
Oh yeah. So this is a very hard thing because in cat, as far as I know, there's no notion of termination, but in a recently developed system called GCAT, I think we can do something there because GCAT has a notion of non-termination, early and late terminations, because it's more closer to a process calculus. It's in between process calculus and Kleene algebra. So yeah, so I think there might be something there, and it's very interesting, I think.
But it's not the cat.
But it's not something cat can
So
do.
it
Yes.
was ad hoc.
Yeah, it is. Yeah.
Yeah. Can you elaborate more on introducing abstract interpretation in this business?
Oh yeah, right. So
you mean that you want a lot an algebra for expressing the fact that two programs have the same abstraction, or something like this?
Yeah, right. So abstract interpretation is a lattice-based system, right? Well, I'm nervous now.
Already the top is an abstract.
Yeah, and it's very order theoretic, and and cat itself has a very nice order theory surrounding it. So I was wondering if there are some connections, and if we can use abstract interpretation to abstract TopKAT, or can we use TopKAT to abstract interpretation in a sense like that?
I've done 2 years ago in SAS.
Okay. Yeah. Great.
Thanks again.
Thanks.